Matter, like a magnificent tapestry, a fabric woven stitch by stitch from subatomic particles, a blanket that makes up the entire universe we experience.
But 100 years ago, matter didn't seem nearly this complex to anyone. With the knowledge available at the time, what we called matter could be easily explained with just electrons and protons.
Unlike the incredibly detailed masterpiece that stands before us today, what we had back then was a much flatter, simpler pattern.
And in the 1920s, with the remarkable breakthroughs of that era, physicists were starting to think they had it all figured out. They believed they were staring at the most fundamental building block of matter.
An atom made of electrons orbiting a positively charged nucleus, and the protons, discovered in 1919, were found in specific numbers within that nucleus. It was this number that made all the diversity of matter in the universe possible.
As you might imagine, abandoning this relatively simple approach wasn't easy. And don't for a second think there aren't conservatives in the world of science.
The more innovative scientists who dared to suggest the possibility of new particles were seen as troublemakers, people who were trying to make things more complicated than they needed to be.
But here's the thing. Those so-called troublemakers are the ones who wrote their names into history. It's because of those mavericks that we can talk about real progress.
Every era has its annus mirabilis, its miracle year.
Take 1543, for example. Andreas Vesalius published his groundbreaking work on human anatomy, etching his name into the history of medicine. That very same year, Copernicus released his masterpiece on the revolutions of the celestial spheres and changed astronomy forever. That's why 1543 is remembered as a miracle year.
Or 1905, one of the most famous miracle years of all. Albert Einstein submitted 4 papers to the Annals der Physik journal, and after that, nothing in physics would ever be the same again. Though it may not be celebrated as widely in the history books, 1932 was also an annus mirabilis. 2 discoveries made that year would shatter the resistance of every scientist who had been fighting against change.
The first was the neutron, hidden inside the atomic nucleus, waiting to be discovered. A particle that would change absolutely everything.
Then came the positron, just like the electron, but with the opposite charge.
And the discovery of the positron quite literally opened Pandora's box. After that, it was like a snowball rolling downhill. Particle after particle was discovered, and with each one we took another step closer to what we now call the Standard Model, the most reliable framework in all of physics.
Along with this, physicists began to understand how atoms actually work, how they decay, how they transform, how they react.
And this path would inevitably lead to the most destructive invention in human history: nuclear weapons.
Until this point, nobody outside the world of science had any reason to care about how atoms worked. But with this devastating invention, everyone would come to understand that atomic physics, for better and for worse, was about to literally change the world.
There's a principle called Occam's razor. It's a problem-solving rule that says you should never multiply possibilities beyond what is strictly necessary.
And that is exactly why it was so difficult to abandon the electron and proton model of the atom, right up until the 1930s.
But that necessity had arrived, and it was knocking loudly at the door. The recently discovered cosmic rays, what they were and where they came from, demanded answers. So did the puzzling existence of isotopes,
elements with identical chemical properties but different masses. These unsolved mysteries created that necessity. The first big step was taken by New Zealand-born Ernest Rutherford. In 1920, he proposed that neutral particles within the atomic nucleus could explain these isotopes. But while Rutherford's conclusion was correct, his reasoning was wrong. He believed these particles weren't new at all, that they emerged from protons in very close interaction with electrons.
But can we really blame him? How do you find a particle with absolutely no electric charge? How do you detect it? How do you prove it even exists? And that's when James Chadwick arrived, working at the laboratory in Cambridge, to pick up where Rutherford left off.
In 1932, he discovered a mysterious radiation that appeared when helium nuclei were fired at beryllium.
And this radiation could only be explained by a particle with the same mass as a proton, but with absolutely no charge.
A neutron.
But Chadwick made the same mistake many scientists make. He failed to grasp just how important his own discovery truly was.
In fact, shortly after, he told the New York Times, "I'm afraid the neutron will be of no use to anyone."
And the acceptance of the neutron would take some time, just as it would be for the positron.
Paul Dirac, an extraordinary genius.
In 1928, he managed to unify quantum mechanics with Albert Einstein's special relativity. Through what we now call the Dirac equation, he described the behavior of electrons in a way that satisfied both theories at once.
But there was a strange detail in Dirac's equation, one that even he found curious. Buried within it, a new positively charged particle had revealed itself.
At first, everyone, including Dirac himself, assumed it was simply the proton. But this particle had the same mass as the electron, and protons are 2,000 times heavier than electrons.
Meanwhile, at Caltech, working completely independently of Dirac, another scientist named Carl Anderson was studying cosmic rays using a device called a cloud chamber. And in that same year, 1932, his experiments led him face to face with a positively charged particle that had exactly the same mass as the electron.
It didn't take long to realize this was the very same particle that had appeared in Dirac's equation. He even captured a photograph of it, and this particle would be given a name, the positron.
And with this discovery, the doors to one of the most mysterious fields in all of science would swing wide open: antimatter, a topic we've explored in detail in one of our other videos.
It was such a monumental step that years later, when Dirac was asked why he had hesitated to propose this new particle himself, he had a disarmingly honest answer: pure cowardice.
And the enormous energy potential of the atom was about to be unleashed in a way that could never be undone.
We had seen the first hints of this in radioactive decay. It was clear that the atom harbored an incredible amount of energy within itself, just waiting to be released. Despite radioactivity being discovered in 1896, this potential had waited nearly half a century to be unlocked. And that's exactly why the discovery of the neutron was so important. It was like the key to a box that held all this power inside. Because with the discovery of the neutron, what we know as splitting the atom became a reality, and with it, the ability to transform one element into another. Just 1 year after the discovery of the neutron, Hungarian physicist Leo Szilard predicted that neutrons could be used to split atoms, and that this could be used to build an atomic bomb. In his own words,
The idea suddenly came to me. If we could find elements that could be split by neutrons, and if those elements released two neutrons when they absorbed one, a sufficient amount of this process could start a chain reaction, and the energy released, well, you know, could be used as an enormous bomb.
It was one of the very first official descriptions of a nuclear weapon.
And he was right. Because neutrons carry no electric charge, they could penetrate atoms with remarkable ease.
In 1934, Italian physicist Enrico Fermi and his team began firing neutrons at various elements, producing entirely new radioisotopes. Each isotope had a different number of neutrons in its nucleus, and those numbers determined which isotopes were radioactive and which were stable.
Another study that inspired Fermi came from a familiar name, Irene Joliot-Curie, the daughter of Marie Curie. In 1934, together with her husband, Frédéric Joliot-Curie, she succeeded in producing the first artificial radioactive isotope. Fermi was conducting similar work.
The ultimate goal at the time was to find something beyond uranium, the heaviest element then known on the periodic table.
And at this stage, one of the most important, yet most unjustly treated figures in the history of science would step onto the stage. Lise Meitner.
Born in Austria to a Jewish family, Meitner was forced to flee Nazi Germany in 1938 and resettle in Sweden.
Meitner continued her work in Sweden with her nephew Otto Robert Frisch, and through their neutron bombardment of uranium, Meitner, together with Otto Hahn and Fritz Strassmann, would make a discovery that would change the world.
What appeared was barium, an element far lighter than uranium, and what had just happened was this. Lise Meitner, together with Hahn, had discovered nuclear fission.
During the Christmas holiday of 1938, Lise Meitner had split the atom.
Then, in 1944, only Otto Hahn received the Nobel Prize in chemistry. Meitner's name was never even mentioned. And it doesn't stop there. Over her lifetime, Meitner was nominated for the Nobel Prize a staggering 48 times. She never won, not once. It remains one of the most controversial oversights in the history of science, and there are many reasons behind it.
But the biggest reason was this. Nuclear fission, the splitting of the atom, had taken the entire scientific community by storm. When Niels Bohr announced it to the world, one thing became devastatingly clear. The enormous energy hidden within the atom could now be harnessed. And that meant atomic bombs and nuclear weapons were now on the horizon.
On February 11, 1939, the Science newsletter published a story with the headline, "Atom Energy Released." The article noted that scientists and the public alike were somewhat worried about this development, which was being called a revolution for civilization. They feared that atomic energy could be used as an explosive military weapon.
The fact that the article called it somewhat worried, that it mentioned it as merely a possibility, would unfortunately change nothing. The greatest destruction, the greatest debates, and the greatest regrets in history would follow these developments. And that is exactly why Lise Meitner would never receive the Nobel Prize, because she saw this possibility clearly, and she refused to participate in what were being called nuclear energy research programs in America.
Just like many other scientists who knew their work would be weaponized.
Just like many other scientists who contributed with the best of intentions, and then lived to regret it.
This destructive story of the atom and every single event, person, and institution mentioned in it is entirely real.
Stay tuned.
And as always, until we meet again, glad you're here. Much love.